Okay, today we're going to go over derivatives and antiderivatives of trig functions. Now, this video serves as a precursor for the video I'm going to upload next, the topic of which is going to revolve around trig substitution or theta substitution. And it's quite difficult, and there's quite a bit of background info you need to know as well. And so that's why I'm uploading this video. I might as well point out that there aren't going to be any practice problems with this video, as it's purely just informative. And I'm really just uploading this so others will just gain the knowledge they need to, such that they'll be able to understand next video's topic. And a lot of the stuff I'm going over has been featured in past videos as well, so it would just be redundant to post practice problems. And that's why I've decided to omit them for this video. Okay, so this is the derivative page. On the left, you have your typical trig functions. On the right, you have your inverse trig functions. We might as well begin. Hopefully you're familiar with the derivative of sine x. It's cosine x. The derivative of cosine x is negative sine x. One thing that's worth pointing out is that the derivative of any trig functions, whether inverse or regular, that starts with c, will have a negative derivative. So you can see that here, the derivative of cosine has a negative sine x. Cotangent has a negative here. Cosecant has a negative here. And that pattern follows over to the inverse trig as well. So I'm just pointing that out now. So we may get into at this point, we're probably getting into the derivatives that you may be unfamiliar with. The derivative of tan x is secant squared x. Now, there's a popular mnemonic to memorize this. When you go to the beach, you get a tan, and a tan is sexy, sexy. So the derivative of tan is sexy, sexy, also known as secant squared x. Whereas the derivative of secant x is secant x tan x. Because what's sexy? A sexy tan. So the derivative of secant x is secant x tan x. Now, the derivative of cotangent x is negative cosecant squared x. And something that's sort of worth pointing out is that trigs sort of have an alter ego in a way. They have a similar trig function that begins with a c in a way. At least that's how I try to remember the derivatives. For instance, the opposite of sine is cosine. The opposite of tangent is cotangent. The opposite of secant is cosecant. Now, this really only holds true for when finding the derivatives. So if you're finding the derivative of tan or cotangent, naturally you're going to throw a negative in the derivative because it begins with a c. But you're also going to throw in a cosecant squared x. Now, this, of course, may look similar to the derivative of tan x, where the derivative is secant squared x. But in place of secant squared x, you're going to put cosecant squared x, or more specifically, negative cosecant squared x. Now, the derivative for cosecant x is negative cosecant x times cotangent x. And you can see that, as I said earlier, these trig functions sort of correspond, I suppose. The trig functions that we begin with c's that have an alternate trig function that doesn't begin with a c have similar derivatives, if that makes sense. Okay, so at this point, we're going to get into the inverse trig functions. Now, you can represent an inverse trig by either throwing the prefix or the prefix arc at the beginning of the corresponding trig function. For instance, if you're the inverse trig of sine x is arc sine x, it can also be represented as sine to the power of negative 1x, or not really to the power of negative 1, but inverse. So I, again, just thought I would point that out. The derivative for arc sine x is 1 over the square root of 1 minus x squared. The derivative for arc cosine x is negative 1 over the square root of 1 minus x squared. Now, these are somewhat difficult to memorize. We're really only going to see arc sine x, arc cosine x, and arc tangent x. And even then, you're rarely going to see arc cosine x. And a lot of these have very similar derivatives. For instance, arc cosine x and arc sine x are the same, with the exception of the negative 1, or the multiplication of negative 1 for arc cosine x. Now, the derivative of arc tangent x is 1 over 1 plus x squared. You may notice that the derivative of arc cotangent x is negative 1 over 1 plus x squared. Now, the derivative for arc secant x is 1 over the absolute value of x times the square root of x squared minus 1. And the derivative for arc cosecant x is negative 1 over the absolute value of x times the square root of x squared minus 1. Okay, so this is the antiderivative page of your common trig functions. And now I decided to exclude arcs or inverse trig functions, as you really never see them in calculus. I've never come across the antiderivative for a trig function, neither in calculus AB or BC. So I decided to exclude those. They're actually quite simple to find and memorize. They do certainly exist, but they're just not here. So before we take a look at the larger list on the left, let's take a look over here. These may seem familiar. The antiderivative of cosecant x squared is tangent or tan x plus c. If you were to take the derivative of both sides, you just end up with the derivative of tangent x equals secant squared x. So this is really just like an antiderivative is really just the inverse of a derivative. And so that's really just what I'm showcasing here. You've seen them before on the page prior, if you recall, but I decided to put them in anyways. Now, on the left side of the page, we have the antiderivative of cosine x is equal to sine x plus c, c being any value, as you probably already know. The antiderivative of sine x is negative cosine x plus c. If you're ever concerned about whether the antiderivative has a negative or not, if you're ever concerned about whether your antiderivative is correct, just take the derivative of it. So the derivative of negative cosine x, for instance, is going to be sine x plus c. Same goes if you were to find the derivative of negative cosine x plus c. Since c is a constant, the derivative of it is going to be 0. Now, this is where it gets a bit confusing. And this is really why these next 4 equations are the reason I created this video, because you sometimes see them in trig-sub. So the first of which is going to be the antiderivative of tan x, which is natural log the absolute value of secant x plus c. Now, normally when you're finding the derivative of a trig function that begins with c, you're going to include a negative in the derivative. However, this isn't the case with integration. The antiderivative cotangent x with respect to x is equal to natural log absolute value of sine x plus c. The antiderivative of secant x dx is equal to natural log absolute value of secant x plus tan x plus c. The absolute value of secant x, the absolute value of cosecant x dx equals natural log cosecant x, natural log absolute value of cosecant x minus cotangent x plus c. So if you're concerned about these, you don't really have to worry. In fact, these 3, I've never seen them. I've really only seen this tangent x, the antiderivative of tangent x. And even then, this makes sense. The absolute value of natural log, which I'll show right here, natural log absolute value of secant x plus c, is pretty simple to find. And you can use this if you're ever unsure whether your antiderivative is correct. So the process of finding the derivative of a natural log is simple. You have to employ the chain rule. What you're first going to do is you're going to write 1 over the function on the inside of natural log, and that's secant x times the derivative of the inside function, which is going to be the derivative of secant x, which, if you recall, we went over on the page prior, is actually secant x times tan x, because a tan is sexy, and therefore, what's sexy? A sexy tan. So that's how we end up with this product over here. We can cross out the secants, and we end up with tan x. And that is how the antiderivative of tan x is natural log secant x. And of course, you can't take the derivative of a function. I suppose you could take the derivative of a function and end up with tan, but that's not really the proper way of finding the antiderivative. You're going to have to go through a lot of trial and error, and it's best just to memorize this formula over here. But that's it for today's video. Again, it's just a precursor to the next one. If you have any suggestions for future videos, please put them in the comments below. Thank you.